Hello and welcome. If you're a technician working on the latest agricultural and construction machines, you know just how incredibly complex they've become. Today, we're going to crack open the blueprint for how these intelligent machines actually think and communicate. We're talking about the IEC 614991 standard, the rulebook that directs that complex dance between dozens of control units in the very machines you work on every single day.
Okay, let's jump right in with a problem that every master technician knows all too well. You look at a new combine harvester or a high-tech excavator, and you realize there isn't just one central brain anymore. Nope, it's a whole network of over 50 specialized control units. So how in the world do they coordinate everything to harvest a field or dig a foundation without tripping all over each other?
Well, that exact complexity is why the old way of thinking, with one single powerful controller running a rigid, continuous loop, it just doesn't cut it anymore. With so many different components that need to talk and coordinate, a centralized approach is just way too slow and inefficient. We absolutely need a new architectural model to manage all this distributed intelligence. And this isn't some abstract theory. This standard is the practical, essential rulebook that allows components from dozens of different manufacturers to all speak the same language and work together seamlessly in a single complex machine. It's the very thing that makes true system integration even possible. So the crucial point here is understanding the hierarchy that this standard creates. To really wrap our heads around it, we're now going to zoom into a smart machine and break it down layer by layer, starting right at the very top.
At the highest level, we have the system. The standard defines this as the entire collection of communicating parts. Imagine a combine harvester, a tractor with a smart implement, and a central farm management system, all sharing data and working together. That entire fleet with all its connected components, that is the system. Let's go one level deeper, down to the device. A device is a single, independent machine within that system. It's your combine harvester with its specific job. It's one machine in the fleet, a single node in the network. And now let's pop the hood on that device. Inside, it's made up of multiple resources. These are the actual brains for specific jobs, like the control unit for the engine, the one for the threshing unit, or the one for the GPS. Each resource has independent control and can run its own part of the machine's application. For example, the threshing unit's controller could be responsible for monitoring grain loss and adjusting the drum settings in real time. Okay, let's dive into the absolute core of the control logic, the function block. If the system is the body and the resources are the organs, then the function blocks are the DNA. They are the fundamental building blocks of any application that runs on a resource. So, what does that actually mean? Well, to put it simply, a function block is a reusable piece of software code that performs a specific task. And the key part is this: it has its own memory. It remembers its state from one moment to the next. That means it can keep track of how many times an event has happened or what the last sensor reading was. Now, what's really interesting here is that there are two main flavors of function blocks. You've got your basic function blocks. These are the indivisible muscle cells that do one specific job. A perfect example, and one we're going to focus on, is the ECTU, an event-driven up counter. Its only job is to count up by one every time it gets a trigger event. In a combine, an ECTU could count how many times the grain tank is unloaded, which could then be used to calculate a field's total yield. Then you have composite function blocks, which act like a manager organizing a network of these basic blocks to carry out a more complex operation. And this right here, this illustrates the biggest paradigm shift away from older control systems. Instead of constantly running in a rigid, power-hungry loop, checking everything all the time, this architecture is event-driven. It waits for a trigger. The standard defines an event as an instantaneous occurrence. It's the trigger. It could be a signal from a sensor that the green tank is full, a button press in the cab, or a data message from another controller. It's a signal that says, hey, pay attention, you need to do something now. And here's how it all works. Let's stick with our ECTU example. An event arrives at the ECTU function block, triggered by a sensor that says the grain tank has been emptied. The block's internal logic, its execution control chart, you can think of it as its internal rulebook, tells the resources scheduler, I need to run this specific piece of code. The code runs, adds one to the counter, and when it's done, it generates a new output event to trigger the next block in the chain.
This process is incredibly efficient and responsive because action only happens when it's actually needed. So, we've chewed through the theory, but why does any of this matter when you've got grease on your hands, a customer on the phone, and a harvest deadline breathing down your neck? Here's the bottom line. Knowing this architecture gives you a completely new diagnostic tool. When a machine is acting up, the problem might not be a broken cable or a faulty sensor. It could be a logic error, an event that isn't firing correctly, or data that isn't flowing between function blocks. For instance, if the yield monitor in the combine isn't working, knowing the standard allows you to trace the data flow from the grain tank sensor through the ECTU function block all the way to the display in the cab. This understanding helps you diagnose the machine's nervous system, not just its mechanical parts. It's what makes you ready for the future of diagnostics.
And that's the key takeaway. The next time you're facing one of those baffling problems where all the parts seem to be fine but the machine still doesn't work, take a step back and think about the architecture. Is there a breakdown in the flow of events and data? Because understanding the blueprint is the first and most critical step to solving the puzzle of a modern, intelligent machine.